Now we want to talk about the types of intermolecular forces. We already established the idea of what the importance of intermolecular forces, what they are, and we said that they're always attractive and they're based around interactions between positive and negative charges. And that what underlies the positive and negative charges on a molecule is the polarity of that molecule. Is the molecule polar or not? So it's going to be really important that we know how to do that moving forward. Participation 114, question 1. Classify each compound as polar or nonpolar. Then I have three Lewis structures here, so A, B, C. So all of this is question 1. So there's going to be three kind of answers, 3 words or ideas that are part of question 1. So I want you to classify each compound as polar or nonpolar. So the first question on participation 114, due Friday, January 14th over on Blackboard. The link to the assignment is right below the links to these videos. So this idea of molecules being polar or not is really important because that's the main driving interaction between molecules in a bulk phase. When they're all jammed close in together, the question is, are they, where are the positives, where are the negatives? Because we know that like charges are going to repel each other. So there is some repulsion on that, but then there's also this opposite attraction. And so what the molecules do is they don't just all jam together and take whatever. The molecules rearrange themselves, right? Pointing opposite ends at each other. And so these are called dipole-dipole interactions. So these are the attractive interactions between molecules because they are polar. These are molecules that have permanent dipoles, that they're always polar. That's what that means. And so they're interacting in that way. And so the reason why it's attractive is because the molecules just arrange in such a way that the positive ends point at the negative ends. So we can see this is shown here for HCl, which is something we talked about as being a polar molecule. It's only 2 atoms, and because they're different, it's going to be polar. So one quick note on notation here. You can start to see there are dashed lines in here. Dashed lines mean it's an intermolecular interaction. We are going to reserve solid lines for chemical bonds. So the solid line, the hyphens in between the hydrogen and the chlorine, that indicates that those molecules are bonded together. Then the dashes just imply what interactions there are between different molecules. So they're always going to be dashed for intermolecular forces. So this is just 5 molecules. You can see they're kind of arranged such that the plus is lined up with the negative. This contributes to an order that is going to be maintained throughout the material. So you're going to have these kind of repeating patterns such that these dipoles all are interacting with each other. Everything is lined up. Our second type of intermolecular interaction then is called the hydrogen bond. And I'm going to tell you right now, hydrogen bonds have a confusing naming convention. There is no getting around it. It just is confusing. So we just want to be careful whenever we're thinking, we're talking about it. We should kind of always have in the back of our mind, let's be careful when we're talking about these. So hydrogen bonds are still dipole-dipole, still the interaction of dipoles, but importantly, they're interaction between bond dipoles, not entire molecules anymore. A dipole-dipole was, the positive side of the molecule, negative side of the molecule. Here we're looking at bonds. And so this molecule right here, these are water molecules. And so what's going on, the hydrogen bond is the intermolecular force. So this right here, that is linking these 2 molecules. You can see the positive on the hydrogen is with the negative touching the negative on the oxygen or interacting with. That intermolecular force is made possible because of this covalent bond between the hydrogen and the oxygen. And so this can happen anytime you have a hydrogen atom that is covalently bonded to oxygen, nitrogen, or fluorine. Okay, and so some of the naming convention that we're talking about, this is a covalent bond featuring hydrogen. Because that covalent bond is to an oxygen atom, you can form the intermolecular force that is a hydrogen bond. So hydrogen is an important part, but the hydrogen bond is an intermolecular force. It's not a covalent bond. This is an old-timey kind of naming system that's just stuck around. And you'll note it's still positive linked up with negative. The reason why these get a special name is that these are particularly strong, particularly important. You'll notice water is here. Remember, water is a very important molecule. We want to remember, if you remember one thing about polarity, that water is polar. If you remember one thing about hydrogen bonds, it's the fact that water can form hydrogen bonds. What's special about oxygen, nitrogen, fluorine? Well, if you remember based on our periodic trends, if you look at the periodic table, those are all near the top right of the table. And so there's a couple trends that they're near the extreme of. First is the extreme of electronegativity. If you remember, fluorine is the most electronegative, so that's really important here. So that what that means is that these are slightly negative and slightly positive, but they're a bit more slightly than your average dipole. These are quite large dipoles that we're dealing with. These are pretty big charge separations. The other very important thing is that O and F are small. If you remember atomic radius, you get smaller as you go to the top right of the table. So helium's the smallest atom, but it doesn't form bonds. But so nitrogen, oxygen, fluorine are really small. What that means is that this distance between the positive and negative is relatively short. So strong charges, short distance makes for very strong interactions. And so these molecules are going to interact in such a way that maximizes those interactions. So just like dipole-dipole, that molecules would arrange their positive and negative. In the case of hydrogen bondings, these molecules are going to arrange these individual bonds to line up in such a way that they get these sorts of interactions. And these are particularly strong interactions that hold these molecules together. And so because they can get really close, they do and maintain that. As you'll note, like chlorine is really electronegative. It's right below fluorine in the periodic table, but it's big. It's quite a bit bigger than fluorine. You just can't get close together. You can't really get that strong interaction between molecules, even though the charge separation is quite large. So if we want to know whether or not a molecule can form hydrogen bonds, it's all based around the Lewis structure. And what you are looking for is not just hydrogen and oxygen in the molecule, but they need to be explicitly connected to each other. I have oxygen in this molecule, and I have plenty of hydrogen atoms, but importantly, the hydrogen atoms are not covalently bonded to the oxygen. Therefore, this molecule cannot form hydrogen bonds. If that hydrogen is directly covalently bonded to the oxygen, they are sharing electrons, they are unequally sharing electrons, that allows for the formation of hydrogen bonds. So when we look at just the overall molecular formula, we can't diagnose whether or not a molecule can form hydrogen bonds. We would need to look at the Lewis structure. How are the atoms arranged? How are they connected together? And that's going to inform whether or not we can form hydrogen bonds. Let's look at an example. Which of the following molecules is capable of forming hydrogen bonds? If it can, draw two molecules forming that hydrogen bond. If we want to know anything about intermolecular forces, about a compound, we always want to start with drawing the Lewis structure. All properties are going to come from the molecule. We're interested in kind of all these molecules together, but we need to know what one molecule looks like. What is the Lewis structure of that molecule? And then, is there an HN bond? Is there an HO bond? Or is there an HF bond in the molecule? And if yes to that, then you can form hydrogen bonds. CH3OH. So one thing we want to practice, how do we draw Lewis structures? If we look at CH3OH, this is a condensed structure of an organic molecule. I have the C part and I have the O part. We know that those are going to be linked together, and then we just put our hydrogen decoration. C part and the O part. This is called methanol. This is a common alcohol. And so we can see here is our Lewis structure for methanol. So the question is, can this form hydrogen bonds once we have the Lewis structure? O is covalently bonded to H. Yes, this can form hydrogen bonds. Once we see that feature in the molecule, we are done. So now the question is, how would we draw these molecules interacting with each other? Still going to use the Lewis structures, and it's going to be based around the dipole of the individual OH bond. That is the strong interaction. That's what hydrogen bonds are about. So how are they going to arrange that? Well, what's going to happen is the positive of one molecule is going to be attracted to the negative of another molecule. So that methanol molecule is going to come in where the positive, which is the hydrogen side, lines up with the oxygen side. You don't necessarily need to know which side is positive and negative. In the case of hydrogen bonds, hydrogen is always positive, the other atom is always negative. But we know that's what it's going to look like, and there is the hydrogen bond. So this is our kind of Lewis structure schematic. Importantly, with hydrogen bonds, the focus is on that one covalent bond, not the whole molecule. The whole rest of the molecule just deals with it because this is a really strong interaction. Now, these Lewis structures are not showing the real shapes of molecules. We know that the oxygen is actually in a bent local geometry where, it's got the lone pairs taking up space that are important. So they're kind of at a bent angle. And so what ends up happening is you have multiple kind of linkages together. So you can kind of see this molecule, the hydrogen bond kind of comes up to that molecule. You get a link up to that molecule, and you get a link up to that molecule. They're just kind of moving along, shuffling and kind of through there, and you get these kind of chains of molecules where all of these hydrogens are kind of linking in together. And you can even kind of see that in this case of these right here, that you have hydrogen to oxygen and hydrogen to oxygen. Same idea in both of those cases. And that's fine. They're all linking in together. It's just positive to negative. H2S. If we want to look at the Lewis structure for H2S, there are no nitrogens, oxygens, or fluorines in this molecule. There's no hydrogen bonding. You actually don't even need to draw the Lewis structure. If you don't have hydrogen is another thing. Molecules without hydrogen cannot form hydrogen bonds. No nitrogen, no oxygen, no fluorine. You don't need to draw the structure. You have to have those together. You'll need to draw the structure to figure out if they're bonded together. But if they're not in the molecule, then they can't be bonded together. CH2O, this is called formaldehyde. So we can see we do have oxygen and hydrogen in the molecule. If we want to think about how I kind of came up with drawing this Lewis structure, we can use kind of the idea of a condensed structure. The carbon links in, then there's the oxygen, carbon and the oxygen. When we're also drawing Lewis structures, we also know that the first atom is the central atom, except if it's hydrogen, and the other atoms go on the outside. So you can follow some rules based on that, adding in lone pairs and forming double bonds as necessary. I got my Lewis structure. I want to know, can this thing form hydrogen bonds? Well, I have the necessary things. I have hydrogen, I have oxygen, but importantly, they're not bonded to each other. So this molecule cannot form hydrogen bonds. They're there, the parts are there, but I had to draw the Lewis structure to diagnose that I can't form hydrogen bonds. This molecule is polar, and so they would interact by being polar molecules. So we can think of doing the same thing. How would they line up? And what ends up happening is just that positive end goes into the negative end, and that kind of is a chain that will just go along. Finally, we have dispersion. Okay, so dispersion is another type of intermolecular force, the third type that we're going to talk about, third and final type. And it's another attractive force, and it's still between dipoles. Dispersion is still between dipoles. You'll note everything is an interaction between dipoles. That's how you get these charge separations. But you'll note this time it's for temporary dipoles. So when we talk about a polar molecule, what we mean is that there is a positive end of the molecule and a negative end, and they are always there. We would say they are permanent. So temporary dipoles are the opposite of that. And so one of the things we can imagine, if you're interacting between temporary dipoles, it's probably pretty weak. Dispersion occurs for every single molecule. Every single molecule undergoes dispersion when it interacts with other molecules. This is the only intermolecular force for non-polar molecules, right? Polar molecules did dipole-dipole. Some polar molecules do hydrogen bonding. All of our non-polar molecules, all they can do is dispersion. It's important to note polar molecules still do undergo dispersion and interact with other molecules in terms of dispersion. So what's a temporary dipole? So you have two non-polar molecules. For example, H2. It's just two hydrogen atoms. They're the same atom, So the polarity of the molecule is based on the polarity of the bond. So boom, nonpolar molecules. We would not expect them to interact with each other by dipole-dipole because there's no permanent dipole. But the molecules around one of the molecules, can undergo what's called polarization. They form an instantaneous dipole. Okay? Instantaneous. If you think about that word, in an instant, they form a dipole. This is because, right, electrons are freely moving around a molecule, and what happened in this case is normally they're equally distributed, but you got kind of a traffic jam. There's more electrons over here. That means there are less electrons over here. There's a positive end of this molecule and a negative end of this molecule. It's not caused by any sort of underlying electronegativity. There's no underlying electronegativity or kind of poles that's underlying this. It's instead random chance. It just boom, happened in an instant. Well, what ends up happening is that induces a dipole on the other molecule because there's a positive side right here, so that the electrons in this molecule want to start hanging out around that positive in the other molecule, leaving a positive side over here. So one molecule forms an instantaneous dipole, the other molecule forms an induced dipole. It's been created, outside forces have created this dipole, and that allows for, hey, we got a positive interacting with a negative. That's attractive. And so that is how dispersion works. You will note, it's kind of a long-winded explanation. It requires multiple probabilities. You have to have the instantaneous occurrence of this creation of a dipole, and then there has to be another molecule nearby that can be induced in order for dispersion to occur. It does happen. If you think about, there's a lot of molecules in a bulk phase. They got multiple electrons. It is rare, but it's just you have so many chances that it happens. And there's a lot of molecules. There's generally a decent chance that you get inducement of a second dipole, but they're both temporary. Eventually, these electrons will just go back to being balanced. They don't stay polarized. Eventually, this whole thing is going to wipe out and look just like this over here again. And then they're not attracted to each other. So when you have a nonpolar molecule, they don't have the permanent dipoles that would cause organization. It has to be these temporary dipoles, instantaneous and then induced. All right, so all of these kind of intermolecular forces we can arrange based off of the relative strength. The weakest are these dispersion forces. You'll see it says London here. Other places you'll see van der Waals. Those are names of scientists who came up with these. I'm just going to call them dispersion forces to be neutral. I'm not going to pick who came up with them first. But they're the weakest. And there's the energy scale over here. This is in kilocalories per mole. Bigger numbers mean stronger interaction. So dispersion, pretty weak. Dipole-dipole, we kind of continue with our next highest. Strongest, we're moving up kind of in an order of magnitude, higher in dipole-dipole interactions. They're both dipole-dipoles. One of the things to note, these are just permanent. They're always there. This molecule always has a positive side and a negative side. In dispersion, they're not permanent. That you're relying on that inducement. So it would potentially be the same strength interaction. They're just not always holding the molecules together. And then the particularly strong interactions are these hydrogen bonds. You can see they're even stronger. They go up. Hydrogen bonding. Those molecules are arranging to have those bonds line up in such a way. One thing to note, these are the intermolecular forces. All of these intermolecular forces are much weaker than any bond, right? These intramolecular forces, the ionic bonds, covalent bonds, are way stronger. They're, one or two orders of magnitude, right? Times 10, times 100 times stronger. Much, much stronger. And so these intermolecular forces, we always want to remember, they're just how atoms and molecules are going to arrange together when you put them in, say, a solid and a liquid, where they're touching each other. But they're not, your molecules aren't going to break apart in order to form a hydrogen bond. Dimethyl ether, which can't form it because they're not going to rearrange bonds to form hydrogen bonds. That's never going to happen. Instead, you're just going to, how the molecules kind of sit next to each other is going to be affected by these hydrogen bonds.
One video down, already got that first participation question. So that was the first question, was that in slides at the beginning of this video, if you missed it. You're looking for those blue frames. So there's going to be a couple more questions throughout the rest of these videos that you want to also find and get those answered as well. All of that is going to be due on Friday. Also on Saturday, you have the homework due that will cover all of the Chapter 10 content from this week. Post lab due Sunday, kind of wrapping up and analyzing what we did on campus on Wednesday. And then don't forget the introduction discussion board due Sunday. No chemistry to that, just talking about yourself. If you have any questions, let me know. Email, call, text. We can meet online as well. Anything like that, just let me know. Otherwise, welcome to our second set of videos. One down, a couple more to go, getting in here for the lecture. I'll see you in the next video. Bye-bye.